we'll get started. One unfortunate thing is I left my microphone to the computer somewhere else, so speak up when you ask questions because we're using the microphone on the top of the laptop, which is a really bad microphone. So it's good that you're all here today because it's going to be really poor sound quality for everyone else online. So, you know, you do what you can. All right. I'll take, well, let's see, when's homework due? Thursday? All right, I'll take like 3 minutes worth of questions. Project 3? I mean, assignment 2? Class is confused. No questions? Yeah?
Anyone good on both parts?
Both parts? I don't know. I gotta say, yeah. I mean, I know of some people. 20 people have got part 3 or part 2. I don't really know how many people have part 1 100%, but it's probably a good number, I think. Anything else? All right, let's get started. About setuid. So, what's the importance of setuid? Why do we care? What was that? Yeah, our end goal is to get root privileges, but it doesn't necessarily have to be root, right? So setuid means that a program is going to be executing with somebody else's permissions, right? Which is really awesome because then we can use that, and if those permissions are different from ours, like another user, or if they're the super user's permissions, then that's really great as well. So, before we get started in on the attacks, I wanted to take a little bit of time to talk about how do we, yeah?
Do we need to get root privilege?
What?
Do we need the root privilege?
No, I hope not, but if you do, you should let me know, because that would be an unintended vulnerability, so.
I think somebody told me that we have.
No, I don't think so. You've been misled. Maybe some hackers in here are running campaigns of misinformation, right? Deliberately to try to trick you. Yeah.
Because on part 1 you need it. You need root
Yes, on part 1 you're running it as root.
Like I did it in Eclipse, and so I ran Eclipse as root, so I'm just putting it in there. And when I created the project, it made everything that was in that folder have to have root privileges.
Yes.
Which I just kept, but that could be one. I could be some people. The 2 projects are going to be.
They're very different. They're not even being run on the same systems, so yeah. Don't need root for part 2. Or you shouldn't. If you do end up getting root, you should tell me. It's unintended. All right. So so when we compile a program, right, what's the file that's on the system? Like we saw on Friday, the change shell, CHSH, or the PASSWD. What kind of file formats are those? What kind of programs are they? Like, is it a Python file that's doing that? What is it?
Executable binary.
Yeah, it's executable binary. So what kind of format is it in?
Here.
Yeah, so it's an ELF binary. So if we want to try to find some bugs or some vulnerabilities in it, right? Because we know, hey, that's a privileged program. When I execute it, it's running as root. But what do? Do I just like look at the 1s and 0s of the file? I mean, maybe you could do that. So I guess I kind of have it already up here. But what does disassembly mean? Does that mean we like when you get some IKEA furniture and you have to move it out of your house, you have to disassemble it, and then when you put it back together, you have that one piece that doesn't go anywhere? No, nobody's ever done that, it's just me. Glad you're all IKEA experts. So what does disassembly mean?
Breaking down to assembly lines.
Say it again?
Converting it to the assembly lines.
Yeah, so taking in that binary, those 1s and 0s in that ELF file, and converting it back into x86 assembly code. So why is that useful? Is it useful? Yeah, it's a lot easier to read assembly code than it is just the raw binaries, right? But what about, can we take that then back up to C code? Not always, and yeah, it's a lot more difficult, right? Because there's no guarantee that this is actually a C or C++ program, right? So disassembling, the idea is you want to take that program and you want to try to look at the binary program and identify the x86 instructions of that program. Is it easy or is it difficult, and why?
Because there are a whole bunch of sets of opcodes for different hardware implementations, so the opcodes might not match up 100% anyway.
Opcodes may not match up because there's a lot of different hardware. Maybe. I mean, there definitely could be the binary that you want to analyze is for some MIPS machine that you've never heard of, right? But assuming it is for a machine that you know, then what are some properties you can leverage? Yeah, you know all the registers, you know the layout of the machine, you know the mapping between the assembly instructions and their raw hex values, right? So then is it just trivially easy? So where do you start? How do you know where to start?
Processor.
Yeah, just like
This is close to reverse engineering.
close. It's like the very first step of the reverse engineering process, yeah. So how do we know where to start? Where do we start in that binary? The binary is just a whole bunch of ones and zeros. How do we know which ones and zeros to start with?
The main function.
Yeah, so in the ELF file, right? So not even actually the main function of the program, but in the ELF file format, it defines the entry point of the program, right? So we need to be able to look at that ELF file, identify the entry point of the program, and start disassembling from there. So from there, is it trivial? Can we just go through and crank out opcodes and assembly instructions? Yeah.
If the program is written by someone else, we can maybe retrace their steps. But if it's kind of from another compiler, there will be optimizations, all kinds of stuff that.
Yeah, so there could be it could be compiled with optimization flags. So there may actually be things that we're missing when that get compiled away, which we'll never be able to see. It could be obfuscated, right? Which is kind of a similar thing. But just so I guess we can. What's the big difference between x86 and ARM? What are some of the differences between x86 and ARM? Yeah.
Yes, the main thing I realize is I've been doing x86 in ARM, but till like 2 days ago, I didn't keep in mind that x86 doesn't have fixed length instructions.
So what does that mean, not fixed length instructions?
You can have an instruction which is 1 byte, have an instruction which is 2 bytes.
So how big are the instructions in ARM?
32-bit, length of 64.
Right, so assuming 32-bit, right? Every instruction in ARM is 32 bits, right? So then when you're decompiling that, it's kind of easy in some sense, right? You know, okay, every 32 bits, right, there's going to be a new instruction. But with x86 instructions can vary all the way down from 1 byte to 5 or 6 bytes, right? And so, assuming you properly decode the first byte, then you can be good. And so some of these things, the disassemblers work just by linearly parsing the program and saying, okay, start at the main function and just try to decode everything into x86 instructions. So what types of control flow constructs does assembly language have? So we saw there were jumps. What kind of jumps do we have?
Unconditional and conditional jumps.
Unconditional and conditional, right? So some jumps that we jump to all the time, and sometimes that we jump to some of the time. What else?
Go to a label.
Go to a label. It's another fixed, usually constant jump. Yeah.
For ARM,
Mhm.
for the data to bit architecture, I can write PC directly, like the instruction pointer.
Okay, that's crazy. Luckily on x86 we can't actually write to the instruction pointer. So when we do like a call or a jump, most times we specify the address, right? We say, okay, jump 5 bytes ahead or 6 bytes ahead, right? So that would be like a fixed or a direct control flow, like, hey, go to this. Maybe it's conditional, go to this place sometimes. Can we jump to registers? So the value of whatever's in a register? Yeah, so we can actually, with indirect jumps, we can say, okay, jump to whatever's in P8X. So then can we know statically where that jump is going to go?
No.
Possibly, maybe, but we have to do some maybe sophisticated analysis. It could be that that value is computed at runtime based on hashing things and all kinds of crazy stuff. So this actually is one of the things that makes even disassembly difficult, is because we may not know all of the code, the pass through the program. And so some of the tools, the very simple, stupid tools, just do linear disassembly, like just start disassembling bytes. Some are more sophisticated in that they look at the jumps, and so they will analyze one function and then go to each of the jumps and analyze those functions. So they'll do this kind of recursive attempt to follow the control flow of the program. And the one I actually use like a good amount of the time is just incredibly simple object dump. So let me turn on this VM. Object dump is the GNU disassembler. It's incredibly simple linear disassembler. So if I do a.out, so the -d means disassemble every section in this file. So it's going to try to disassemble the whole thing. And I'm going to pipe this through less because it's going to be a lot of stuff. So I can see here that some of these are actually bad, not valid instructions, right? Because it's just trying to interpret bytes as x86 instructions. So if I search for main, there should be a main here. So this is actually, well, let's, I'm going to do M32 for 32-bit. Oh, I may not have the libraries. Ugh. All right. Let's see. This is the problem of doing demos live. We'll go back. We'll not worry about it, that it's not the architecture exactly that we're talking about. Okay, big difference between 64-bit and 32-bit. The R, I actually don't know what that stands for, but I'm going to say it's a really large register. It's 64 bits now instead of 32. But we can see here from this main function, it's decoded, okay, push the register, the base pointer, move the stack pointer into the base pointer, push register 13, push register 12, push register RBX. Right, so we can see that this the disassembler has been able to do this, right? So it's actually been able to try to identify these instructions that are executed at runtime. And so we have calls, and we have compares, and we have jumps. So it's going to jump to this location. So if I searched for 40193B, hopefully I will find that. So this is that label or something that it's going to be jumping from here to do all this stuff. Okay. So this is kind of like the most works. Okay. So there are a lot of disassemblers out there. I'm going to talk about a few of them just to give you some pointers of where to look. Radaware is a whole suite of program analysis tools. It does reversing, some vulnerability analysis stuff, and it does disassembly of binaries, some forensic stuff. Really cool stuff is it has bindings to Python for a lot of these features, so you can use this as a library in order to automatically disassemble a program, to debug a program, do all kinds of cool stuff. It's also free, which is also a cool feature when using these tools. Another like the most popular tool is IDA Pro. So this is the state-of-the-art tool for reverse engineering and disassembly. Like it has a incredibly sophisticated disassembler. It's got a nice graph view so you can see how the control flow goes throughout all those pieces. It can do disassembly for just about every architecture you can throw at it. It will be able to disassemble it. It even supports, well, with an additional plugin, it will even support decompilation. So what's decompilation?
Translate it back to the original source code. Oh, mostly.
Yeah, so not exactly the original source code, right? Because it can't guarantee that. But it will output a C representation of that binary. How close it is depends on a lot of things. You can integrate GDB or other debuggers with IDA. You can also script IDA. The downside is it is very expensive. Anyone want to guess how much just the license for IDA costs? Yeah, like $1,500, I think, for just a license. And the decompiler is like $3,000 to $4,000 per architecture. So x86, ARM, 64-bit. Yeah. The nice thing is there is a limited version that is available for free. So if you want to download it and play around with it, there's an older version that's for free on their website. It's also when you start using it, the user interface is just terrible. Like I just have to tell you that off the bat now. But it's one of those tools that it's like it is the best in its class, and people use it despite the interface being terrible. So there's a whole book on like the IDA Pro book that was written by somebody else, and it's like how to actually use IDA. There's other newer stuff. There's a tool called Hopper that is a disassembler. It includes a decompiler. I don't know exactly how good it is yet. It's a commercial product, but you can use it for free, and it's actually not very expensive. I mean, compared to IDA, everything's cheap compared to IDA. But you can get very far with object dump and your brain. So those are nice things. Okay. Any questions on this before we get onto our attacks? Okay. So we're going to look at a few different attacks against Linux and Unix systems based on all the knowledge we've learned about binaries and the systems. So we're going to talk about all kinds of attacks. So we're going to talk about, so what would be remote attacks against the network service? What was that? DDoS. Yeah, it would definitely be a remote attack. I think, well, we talked a lot about denial of service attacks kind of the networking level. So here we want to try to like take things over, kind of expand our privilege. So why would remote attacks be useful or interesting? Yeah.
I mean, if you could execute remote code, then you could do all those things.
Yeah. Right. So you have how much access? I mean, let's say it's a system. Like, let's think of maybe assignment 2, part 2. Right. What access do you have on that system? Anybody here have a user account on there? Can you SSH in that machine? Can you run arbitrary commands? No. Right? But it's offering you a network service, right? And so if you're able to somehow trick that system into executing arbitrary code that you decide, now you essentially are on that system, and then you could leverage maybe other attacks to gain other visibility on the system. Some of the stuff we'll talk about are some, can be applied even at the operating system level. So why would remote attacks against the operating system be useful?
Specific OS has specific network vulnerabilities.
Mm-hmm. But why would it be useful? Why would it be useful? Why would you attack network services and be done with it?
Multiple hosts.
Multiple hosts? In what sense?
Like, if we know that multiple hosts are running the same OS, we can attack them together.
Yeah, so we're the operating system, right? There's multiple applications running in that operating system. If I just remotely exploit one application, well, then I have the permissions of that application. I can do whatever it can do. if I have the operating system, now I can mess with any application on that system, right? Other kinds of things, even remote attacks against a browser. So the website that you visit may load some advertisement, which loads some unintentionally malicious or maybe intentionally malicious code, which then attacks your browser and then gets on your system, right? So this is another class of attacks that's able to go from remote, right, to you. Then we're going to look at local attack. We're also going to look at local attacks against setuid. Yeah.
What's an example of a remote attack against an OS?
Like a concrete example. They are they're incredibly rare nowadays, but you could. I believe there was vulnerabilities in like the TCP IP stack. And so you take buffer overflow in there, you send data, and now you're executing arbitrary code in the OS's, in the kernel space of that operating system. So you completely own that operating system.
Maybe something like a USB port.
USBs, you still need physical access. So like for here, I'm more interested in like internet accessible stuff. But yeah, even like local printing things, like printing services, I don't know, all kinds of those. Anything that the operating system does, network-wise, oftentimes can be exploited this way. They're very rare because it means you can get to the OS level from completely outside of the system. So it's very rare that you find these type of things nowadays. So when we're local on the system, right, we want to try to exploit setuid applications, and we talked about that because we want to try to expand our privileges in the applications. And we may even want to try to do local attacks against the operating system, right? So see if there's a way. So what are the differences maybe between remote attacks against the operating system and local attacks against the operating system? They're the same, different, more difficult, less difficult.
Remote is more difficult.
Which one?
Remote attacks are more difficult than local attacks.
Remote attacks are more difficult? Why?
You need to get to the network architecture first and then to the OS.
Yeah, so think about the attack surface, right? So what the operating system on the network, right, exposes, if you think about, all of the operating system code where there could possibly be bugs or vulnerabilities, right? The network code is just a small subset of that, right? But now once you're on the system locally, you can make system calls, you can interact with the operating system in all kinds of ways. So the attack surface is a lot more broad there, so you're more likely to be able to find a vulnerability. Okay, so on Unix, right, so on Linux and what we're looking at, right, so kind of as we said, so that almost all of the local vulnerabilities exploit setuid root programs, right? Because this way, so now you don't really worry about the Linux code itself being secure, vulnerable, whatever. It's another application that is necessary for the administrator that's setuid. And the other these are obviously, don't quote me on these numbers, right? These are approximate. The other tiny fraction of vulnerabilities actually exploit the kernel itself. Okay, so we want to exploit setuid applications. What can we do if we're local on the machine to exploit setuid applications? What can we control? Parameters? Yeah, when we call the functions, right, we control the parameters. What else? Standard input, yeah. Any input to the program? The environment, yeah. So it may read from environment variables. We saw that the environment variables are actually in the process space of an executing application. So it can very well be that we can get input into the application that way. So the inputs, we have the command line, right? Any arguments we pass there, the environment variables. During execution, We can actually maybe provide input with file input by specifying certain files. We may be able to somehow modify it if it's dynamically loading libraries, and we're able to influence that process to get our own code in there. Any kind of potentially any socket input, sockets being TCP/IP sockets or maybe Unix sockets. Maybe we're able to write into a Unix socket to get input into the application. And so this is the way you need to be approaching these about how to break these local applications is, okay, what is this program doing? What inputs is it reading from? And how can I influence that? So how does it interact with the environment? How do applications interact with the environment that maybe we can control? Process. So in what sense?
Create, prosecute,
Yeah, so we could,
duplicate.
yeah, so we could potentially, yeah, actually that's a good point, right? So if we are able to run multiple of these processes at the same time, maybe there's a race condition or something there. We could maybe try to start a process, delete it, start another process, and maybe it leaves behind some temporary files. What else?
Dependencies,
Dependencies in what sense?
like we create virtual environments with binaries, so we can replace those since they are local to user directories.
So usually, well, okay. Yes. Okay, let's think about that. Yeah, so maybe through the environment we can influence what things the trusted program runs, right? We can't actually change the code of the trusted program itself. I think the operating system will actually, if we're able to overwrite a binary, it'll drop the setuid bit so it no longer runs as root. I believe that's how that works. So what kind of environment interactions do processes do? What kind of things do your applications do? Read files, open files, right? Can we mess with the file system? Yeah, right? We can create files, they access files, right? Can we trick it to maybe access our file instead of a trusted file that we have permissions to do? With the processes, right? Maybe we can send signals. The process forks other things. Maybe we can influence it that way. And so really what this comes down to, right, is trying to define, okay, what is this application doing, right? We had that abstract model of an application using the operating system, right? But it's oftentimes because of this, just defining, okay, what is the application and what does it do from a development perspective is really difficult, right? Because it can do all these things, it can access all these files, and it could be that by changing one file that it's able to access, we're able to trick it into executing arbitrary code or to doing something on our behalf. So we're going to look at a lot of different types of attacks here. We're going to look at things where we can influence file accesses. We'll get into the details of all of these. We're going to look at command injection and memory corruption attacks. So these are all still incredibly prevalent, even in completely different domains. So for instance, like command injection is still incredibly popular on the web. And memory corruption, even though we've known about these vulnerabilities and the Morris worm was what, 30 years ago, 25 years ago? And it relied on memory corruption vulnerabilities. That's still an incredibly active area of research in terms of attacks and defenses. So people say, oh, great, we come up with this new way to prevent memory corruption vulnerabilities. And then somebody will break it, they'll find other ways around it. So it's very much a cat and mouse game. Okay. So file access attacks. So when you run a command, when you say like a.out or ch shell, chsh, how does bash know which program you want to execute?
Isn't there a default path to a certain binary that it tries to execute?
Yeah, right? So, in general, right, so there's actually kind of two ways to think about this. So one way is when we execute a program, right? So for those, I know some of you for assignment 1, right, your programming language like Java didn't have a system command. So how did you figure out how to execute the right? How did you know? Oh, I guess maybe you probably did something else. Maybe that's not a good example. So one way we'll see, right, is when we want to execute a program, we check in an environment variable called the path to look for which program to execute, right? Path says, hey, these are the program. This is the list of how to look for programs to execute. What about when we open files for reading and writing? If I just say open foo.txt, where's that going to be executed? What file is going to be open? In the current working directory. Who controls the current working directory of a program? The person who executes it, right? So maybe by running our program in a certain folder, right, maybe we could change what files it actually opens and writes. And so this is kind of file access attacks very broadly are all about doing this. Like, can we trick an application into somehow violating the security just by messing with what it's opening, what files it's opening, what things it's reading, all that kind of stuff. Okay, so the most pretty much basic of these attacks that actually still works on a surprising amount of web applications is what's known as the ... attack. So what does ... refer to? Yeah, so in Unix, right, ... so when you're talking about folders and hierarchies, right, what does ... refer to? The current directory, and ... is what? The parent directory, right? So oftentimes, when you want to open a file, let's say from the user, how do you do it usually? You write applications, you open files. How do you do it? Yeah, you get the file path from the user, maybe concatenating some strings together, right? And if the user, or in this case the attacker, right? So we got to be thinking about every time users can give input to our application, this input can potentially be malicious, right? And so this is the way we have to be thinking. And so the idea is if the application is building some path to a file by concatenating values from the users, like for instance in this C example, we have some initial path and then the user file, right? So we're concatenating these values together. And then let's say it opens this path with read write. So am I restricted by this? So some of the things we need to think about, right, is what does this application, by this code, what does this application intend for the user to do? What was it? So if you were coding this application, why would you write it like this? Like what files do you want this application to open? Yeah.
I think you only want the user to open files in a subdirectory under initial path.
Does everybody agree? That you only want, whatever this initial path is, you only want files to be opened in initial path. Do you agree? That's kind of implicit in the security of this application. Yeah?
No, I would give the full path rather.
We did give the full path. We do / initial path, right? So let's say it's like /etc/ I don't know, program1, and then that's where the users store their log files or something. And so this is a way for them to access their log files.
Yeah, but the user file, the user input for the user file name could have an and CD path to other directory.
Yeah, but we're not talking about that right now. Right? We want to think about what was the intention of the programmer by writing that, right? You would probably not, if that was your intent. I mean, what am I thinking? Yeah, we want to try to get to what's the intent behind here, right? And a reasonable, and there could be 1,000 different things and ways to write it, right? A reasonable assumption would be, okay, whatever initial path is, you should probably only open files there in the initial path. Right? But what happens exactly if the user inputs something with ... characters in it? Then what's going to happen? So what can the user make this program open?
Something in the parent directory of the initial file.
In the parent directory? And then what about that's parent directory?
Yeah, I mean it could just go on.
And then could they specify literally any file on the system? Yeah. Right? Like with the ... you can go ... all the way to the root. You can actually keep going. You don't even need to know exactly how deep you are. ... slash ... And then what file do you want to open? etc password, etc shadow if it's a root file. You want to open /home /adamd /ssh /authorized keys file, or maybe ID_RSA for my private key. So yeah, this is exactly what the ... attack is. Right? So the attacker provides file names with parent directories in it, and this allows them to circumvent the intended security policy of this application. The other way to think about it is called the directory traversal attack. Right? And so this works on web applications too. On web applications, if you're writing to a file and you use this, you can put ... to get the application to write to some other file, which maybe you can leverage for other purposes. And so basically, if you're ever, okay, what do we do? So how do we fix this? What are some strategies for how to fix this? Yeah.
String, if path ever contains a ... just ignore it.
If path ever contains a ... ignore it. Is that enough? What do you do? Do you actually ignore it? Accept only absolute paths? In what sense? The whole path, but here I've given the whole path. Right? I've given this whole initial path. Yeah, so there's a couple issues here, right? So one way to think about it is, okay, disallow any ... in the user file, right? But what if the user included slashes, right? Now they can open a file up not just in the initial path. So let's say they can't go out with ... but with slashes they can go to subdirectories, right? Which could be just as bad depending on our application, right? But our security policy is, hey, we really want to just restrict them to this initial path, right? Only in this directory do I want them to be opening and writing files. So yeah, there's two ways to think about this. One way is, okay, we blacklist, we search for bad things in user file. Another way is, okay, we do this concatenation and then we do the security check that says, okay, this had better be in this folder, right? If it's not in this folder, then we stop and we don't do anything. Yes?
As for ... is it just, I think one ... would be enough because it goes back to, it would be suitable because it would go back to the parent homepage. But is it the only thing the application should look for? I mean, aren't there any other ways that the user can escape to the, is it just ...
Yeah, so that's a very good point, and I was trying to think of that too, right? That's another reason why just blacklisting things is dangerous, and taking a whitelist approach is much better, right? Where you only accept known good. So I would do something like, okay, I would check user file for, it's got to be just alphanumeric characters. Right? That's it. A through Z, 0 through 9. If it's anything else, chuck it. I won't allow you to create a file with that name, right? Because yeah, I was trying to think, okay, well, what about if there's a space, like dot space dot? And it could be that maybe, it depends on what's happening here between path and the open. Maybe other things are being applied to it.
That's what we want a dot.
What was that?
What we do want a dot for like an extension of the file name.
Maybe, but maybe I don't want to allow them to do that, right? Because that becomes trickier, right? Then what do you allow, what do you not allow?
We can use also CWD.
Say that again?
If the initial path, we know the initial path, and if we check with initial path PWD is equal to what the initial path is user file PWD is. So if they are different, then we can say that it is not in the same directory.
Yeah. So we can use other functions to try to have the operating system help us determine where this file is. Yeah.
You could also have to worry about doing it your way. It works a lot better because trying to prevent it, you've also got different encoding schemes that you could use and exploit. So you don't use an actual slash, you use pound whatever.
Yes, that's where it gets super crazy. Yeah, especially if you think about like Unicode and UTF-8 and what does the operating system do with that? Does it, maybe it maps all dot characters, maybe there's other dot Unicode characters in other languages that aren't the ASCII dot, but get mapped by the operating system to the parent working directory. Another thing I just thought of is what about symbolic links in that folder that will link you then out of that folder? Maybe there's a symbolic link from inside the initial path to the root or to something somewhere else. So now maybe you can go outside from that. All kinds of issues. So the basic idea is you need to either heavily sanitize that input or use a whitelist to guarantee that there's not going to be, that the user cannot create a file that violates this security policy. There's actually another cool technique, and this is actually what I use in the submission system. So all of the homework assessment stuff is done, so chroot is a system, is it a syscall? Yeah, I believe it's a syscall, so that an application executes with a new root file system. So basically it says, hey, change, so you do chroot / initial path, and now to your application, when it tries to access slash, it only accesses that initial path. It literally, no matter how many dot slashes it does, it can never go outside because to your application that slash is in there. So yeah, this is kind of the chroot was kind of the first. They are also called jails in BSD. It's kind of gone full circle where you first had like chroots, and then you had virtualization. So you're like, oh great, you have all this isolation with virtualization, and now with like containers like Docker and all that stuff, we're kind of coming back to, oh, run the same processes on the same machine, but have them be separated somehow. So when you're running stuff, so even if when you're running your root application, right, for assignment 2, part 1 on the submission system, you're not actually executing in the submission systems directory. You're executing in your own little subdirectory. So you shouldn't be able to go out, but there's always some stuff that could happen. So, especially when you're running as root. And I also am running you as root, but only the capability to connect to a raw socket. That was the other little trick there. So there's other root capabilities that I took away, I think. So it should be less things you can do. And so chroot's also useful for something like a web server, right? So we know a web server should only touch a certain directory. In most cases, it's var www. So if we put our web server in a chroot, now we can guarantee that it's not going to affect anything else of the file system. Okay. Another type of file attacks are path and home attacks. So these are really fun. So path, as we saw, right, affects, so it's an environment variable, and it determines how the shell, right, how bash or our shell searches for commands. Right, so what's the format of path? Yeah, colon separated values of paths or directories, right? So it's from the left, from the first one, search first in that directory for that file name. If you can't find it, look in the next one. If you can't find it, look in the next one. And then if you can't find it, you say that that file can't be found. So the idea is, if the application itself, right, is invoking commands, if our setuid application is invoking commands without specifying the exact path, then maybe we can control it to execute either a different version or something that we control. Right? So specifically, the system calls of exec LP and exec VP, they use the shell path. So you can call it, say, exec ls, and it will look up in your path parameter to try to find the ls program. So if we change our path, right, because we control the path, we control the environment that this program executes in, we can get it to execute our value and not somebody else's value, or our application. So what is the home environment variable used for? Home directory? Yeah, so it specifies the current user's home directory. So how do you usually access that when you're doing file accesses or something? The tilde. Yeah, right, the tilde. And so when the shell sees that, it knows, okay, look up in the environment variable and expand that, or look up in home in the environment variables, expand that to determine where to go. So if an application is using something like trying to access things with tilde slash myfile.txt, right, an attacker can execute that and change the home environment variable to point to anywhere. And so it'll create this myfile.txt wherever we want. Maybe that's a good thing, maybe it's a bad thing. All right, let's stop here for now because I want to come back and show you an example of path and home attacks so we can see what that looks like. So get back on Wednesday.